Participants, now we will be starting with the first session. We have amongst us Professor K.P. Karunakaran from IIT Bombay. He will be speaking on the topic 3D, 4D printing in drone applications. So kindly remain connected with us. Soon we will be starting with the first session. Thank you all. So we are already connected with Professor K.P. Karunakaran. So welcome, sir.
Thank you. Thank you, madam.
So, dear participants, we will be starting with a very renowned, extinguished guest we have, session speaker we have. He is professor in Mechanical Engineering Department at IIT Bombay. So, he will be taking his session, 3D, 4D printing in drone applications.
Shall I share, madam? Go for sharing?
Yes, sir.
Okay. Now that we are almost half an hour behind schedule, should I stop at 11? How is the time adjustments?
So you may continue. It's okay. Because yes, you may continue. You can take half an hour extra, so no problem.
Okay. Thank you very much. Very good morning to everyone. Thanks to Nitar. Once again, I'm here. I was here last week also. I'm trying to share. I hope everything will go well. The organizers feel free to stop if there is any problem with audio visual, because the mutual interaction is something missing for a teacher. It becomes more like a one-way communication. So this is my first PPT. Is it visible, madam?
Yes, sir, it's visible.
Okay, great. I'll go for presentation mode. Just confirm, because sometimes presentation mode doesn't come. It's in presentation mode now?
Yes, sir.
Yes, sir.
Okay,
sir,
thanks a lot.
To kindly click on the hide button also.
Okay, yes, I'll do that. Yes. Yeah, kindly keep giving such feedbacks. I may tend to forget, or I may not get the right feedback.
Sure.
Once again, very good morning to all of you. Thanks to Nitar for this invitation. I basically would like to use, as it was also highlighted by others like Professor Patnaik, the most important thing in these meetings is networking. You know, we have to get connected. Getting, of course, the latest knowledge is the foremost important goal in this. But the second most important thing is networking, you know, with the other participants and the resource persons. And when I say networking, I'm talking about bidirectional networking. I would also like to use this opportunity to tell you all what kind of research we are doing, because we also need a lot of manpower. Today, India is shining. We don't have too much of restrictions on finance, but getting the right manpower is important. So we do need people from various institutes for masters and PhD programs. So this is also a promotional activity for us to tell you what we do and get connected to get benefit from your the human resources you generate at your institute for higher levels. So with this, I'll start. I have made the presentation in two parts. There are two PPTs. In one, I will talk about the preamble, where I will highlight on the various projects we have been doing related to primarily additive manufacturing. I'm a graduate of 1984. Soon after graduation, I had the option of joining Air Force as pilot officer or HAL. So I chose HAL because HAL gave me the opportunity to do a higher study immediately. So I did MTech in IIT Madras. Then I was posted at HAL Kanpur, where I made best use of it. The entire period of 9 years was like a training program for me. HAL had name any facility of advanced technology, it was available in HAL. And I also registered for my part-time PhD in IIT Kanpur. So that way The entire period of 9 years in Kanpur was my training. Finally, I landed in IIT Bombay in 1994. Except the few hours I teach formally to the students, the rest of the time I am a teammate for my students, or I am myself a student. That is how life has been going on for the last 26 years. It's a very enriching research experience, part of which will be shared today. Okay, so I'll start from my drone passion. As I said, I was in the aerospace in the beginning, and although I thought I would become an aeronautical engineer, I landed up as a manufacturing engineer. I don't regret it. I did reasonably well in HL. I got trained in CNC technology. I'm one of the privileged ones to get exposed to India's largest CNC machine. We had 5-axis, 3-spindle CNC machine, which had 70 meters traverse on x-axis. Even today, that is the largest CNC machine. Its unique spindle called a notating spindle. They use the word notating, probably a German variant. So it had a very strange kinematic configuration. So that machine became my inspiration for doing PhD in IIT Kanpur. It was a software-based system where we proposed a 12 degree of freedom system. 6 degrees of freedom go to the cutter, and 6 degrees of freedom go to the work table or work piece. So we talked about 12 degrees of freedom by appropriately arresting them using the rolling contact method. We proposed a CAM model. So that was my PhD topic, more on the hypothetical side. So my CNC passion continued till about 2005. In 2005, I initiated my drone activity. This is probably the first drone developed in India. That was in 2007. We demonstrated it in Agra. This was funded by AR&DB. They gave about 10 lakh money for us to develop and to take part in the competition. 2 teams went from IIT Bombay. My team demonstrated this drone, and another team by Professor Arya demonstrated the small fixed wing system. So I can to some extent claim that, unless there are some counterclaim, that we are the first to demonstrate drone in India. Subsequently, I focused on manned drone. I'm going to show here the manned drone that we developed. Because drone is normally looked as a toy which is fitted with a camera. This is me in my drone. I had a beard at that time, Corona beard. This is a design team. We have no funding, we have no dedicated team. It's a 8.5 kilowatt motor. We use 8 motors. The interesting part is we did not use any advanced materials like carbon fiber or even aluminum. We went for 10 millimeter by 0.5 millimeter wall thickness square stainless steel 304 tubes, because material and geometry together decide the strength of an object. So we went through a lot of finite element iterations to arrive at this particular geometry. So totally our peak power is 68 kilowatt. This is empty flying. This was done just in front of our lab called Rapid Manufacturing Lab. So this is empty flying first time. Even before that, we made few more models which I have not shown in the video. This is me. I'm going to sit in the drone, not as a pilot, but as a livestock. So my pilot, a very excellent pilot, one of the best in India, he handles the remote. The fellow who is bent, so he flies, he controls, and I was sitting in the drone. I was sitting for two reasons. One is I myself wanted to defy gravity. Second, I can't put my young boys into any risk. So this is India's first manned drone. In this particular video, I am livestock. But very recently, I learned the control and I sat in the drone and controlled it. I'll show it in the next video. Okay, so last Monday I did my second flight. Before that, I did a brief flight. So this is last Monday's flight. So before that, we put sandbags in the seat in my place, balanced it, and then we were flying it using remote control on the ground. So subsequently, after gaining confidence, I was able to see. We have a long way to go. Whatever we have made is a baby step. We would like to make baby steps because safety is topmost importance. Probably we'll do the next flight tomorrow. So this is for a very noble cause. When an accident victim dies, people engage with the family for donating the heart, because heart donation, normally death happens by heart failure. In such case, heart is not very useful as a donation. So when brain death happens, that heart is useful. So the availability of, even people like me have donated, pledged our entire body. But unless the death is this type of death, you will not have the heart available. So number of heart donations itself is very, very less. For example, in the Western region, we get hardly 50 donations. There are more accidents, but it's not easy to convince people to donate. Very often they weep and it's a sudden accident. So it's very difficult to convince them about donation. But when they succeed, they get about 50 hearts every year in Maharashtra region. Out of them, 10 of them are lost during transit. So people engage in both cities, the green corridor for quickly moving it on the road, and then an air transport is required to connect. It can't always afford a chartered flight, so people match it with the time of the regular flights. So all these complications lead to about 10 hearts getting lost every year. Only about 40 hearts are available for fitment. Out of them, again, there are probabilities how many will finally survive. So what we proposed is we will develop a flying device which will take off, collect the heart from the terrace of the donor hospital, fly straight to the receiver hospital. But then when you have such a thing by battery power, that will not give you more than about 20 to 30 minutes of flight. whereas we have to cover something like 250 kilometers, let's say from Surat to Mumbai. So about 250 to 300 kilometers. So what currently we are parallel doing is developing a generator set, an IC engine, driving an alternator, converting the AC to DC to the required level. So a set of three things are involved: an IC engine, an alternator, then related power electronics. We are currently developing a 40 kilowatt system. A drone like this will require two of them. And interestingly, we are all focused on money, because we can't afford. These products are available. For example, there's something called E-Hang developed by China, which runs on battery, and there is something called Surefly, which is a hybrid system running on petrol, generating electricity the way I'm proposing. But the problem is these are all very, very expensive systems making use of carbon fiber and other things. So this particular drone with the generator set will not cost more than about 40 lakhs. I'm not talking about the development cost. When somebody tries to sell it finally, I'm hoping that for about 70 lakhs, one should be able to sell a single seater. So you can get down anywhere. Normal petrol will be used. So you can get down in any petrol bunk after an hour of flight and then refill it and then go on further. So this is the dream I have for organ transport. Subsequently, this can be made into a four-seater version where it can act as an ambulance also. I'm not very keen on urban air mobility and things like that, because there are a lot of traffic will happen. So things like ambulance and all, the number is less, and the nobility of the application also will make the permission process little easier. So this is my efforts on manned drone. So normally we don't build the full drone immediately. We start with a scaled version. This is a 400 by 400. We use the same pipe, but in order to make it lighter, we did a lot of laser cutting to make the pipe lighter. And then we test the physical configuration on this. After that only we prove. For example, the center distance between the two coaxial rotors, we did a lot of equations and CFD analysis and all. We have some data are published also. But when we finally tested on this, we found that the distances are not adequate. So we increased it on the manned drone. So a lot of feedback comes when you actually do it on a scaled version. So this is me flying that scaled version. Nothing great, but this is how I started learning. Finally, I migrated to the full flight. Okay, now I switch over to our other projects which are related to additive manufacturing. We no longer want to call it as additive manufacturing. We call it as hybrid manufacturing. In fact, we call right from the beginning as HLM. HLM stands for hybrid layered manufacturing. I've added a prefix here, MSMA. I've added one more prefix very recently. I'll show it after 2-3 slides. MSMA stands for multi-station, multi-axis hybrid layered manufacturing system. The idea of HLM was conceived very soon after I joined IIT Bombay. At that time, we had FDM, fused deposition modeling system, which is a plastic 3D printer, the cheapest possible, affordable for any academic institution in those days. IIT Bombay, IIT Kanpur had a joint project through which it was procured. Even before us, a year before us, IISc bought this. Interestingly, although most new technologies enter the country through academic institutions, through a lot of government funding, interestingly, 3D printing did not come through government funding. The first entry was by a private company called Datar Switchgears. I would like to fondly and gratefully remember their name. The company doesn't exist anymore. It has been absorbed by L&T, and that is still there in Nasik under the banner of L&T. So I visited the company at that time along with my Guruji, Professor Dande. So we asked him, he told us that the machine is used only for 3 days in the whole month. That is how most prototyping facilities work in the design environment. Most of the time, the prototyping machines will be idling. Rest of the time, the engineers are working on the development. So, but you have to keep them active. So you have to keep on firing some dummy jobs so that the machine is kept active. So they told us, it was a very complex machine among all 3D printers that is known as photomasking machine. It used a liquid photopolymer, and it was a flashlight with a photo mask between the liquid layer and the light source, which created the XY geometry. So that was known as photo masking. Another name is solid ground curing, SGC. It's an Israeli machine. While most 3D printers come from USA, there are a few interesting machines, even software, that come from Israel. Even in defense, Israel does a lot of interesting activities. So they had that particular machine, and it had a lot of systems. It has wax dispensing, it has polymer dispensing, it has face milling, it has a complete photocopier system was there, because the photocopier system creates the mask, the optical mask. So there were several subsystems, something or the other used to go wrong. So it was very important for one to keep the machine running and idling. So I like a very innocent fellow, I asked him, why don't you allow others to use the machine? His answer, he is not an engineer. He was a commerce graduate. He told me, sir, we are the only people to have this machine. We are able to cut down our cycle time in a big way, which our competitors are not able to do. So if I allow them to utilize this machine, indirectly or directly, I'm actually creating a competition. So I prefer the machine idling rather than giving to somebody else. But they used to give it to people who were in the medical field and other non-competitive fields. People who don't compete with them. So they were using it. Nevertheless, the machine was idling for most part of the time. So the bottom line is, very often, even in our academic environment, I see that our machine doesn't run, is not utilized for a long time. And when you really want to use it, the machine is not working. So we keep telling the students to keep firing some dummy jobs. So if this is a 3D printer or any prototyping machine, is like a fire engine or an ambulance. You may not have the utilization very high, but you have to make sure that the equipment is in use. Okay, I digress a little bit. I'll come back to this particular system. We started with arc-based cladding. We again were biased because we were used to FDM. FDM used filament, white color filament, plastic or polymer filament as the raw material. And if you look at a MIG welding process, there again use similar wire. So our concept was simply adopt the plastic 3D printing for metal 3D printing. In other words, we were inspired or biased by FDM when we chose our arc-based additive manufacturing process. So essentially ours is a cladding-based additive manufacturing. In those days, a lot of people went for laser-based cladding because laser is known for very precise cladding with less amount of heat input and all that. But I was very young, funding was not very easy, so we decided to go for MIG welding. So what I'm trying to highlight here is our choices may not be always the right choice. Our environment and our mental limitations force us to choose them. Since I was very familiar with fuse deposition modeling, the MIG process was my natural choice. I could have gone for powder bed technology, but MIG process was my natural choice because I was biased towards that. I could not think beyond that. And we went for MIG because we didn't simply have money. Now, since we had to go for MIG, MIG could never produce a, 0.1 millimeter layer thickness or 0.2 millimeter layer thickness. The layer thickness were of the order of 3 millimeters. Now, when you make a 100 millimeter component out of a 3 millimeter layer thickness, you can think of the kind of stair-step effect it will lead to. So we had to naturally combine subtraction on the same machine. So that is how we started hybridizing material addition and material subtraction. I would like to submit to you or confess to you that it was not by my choice that we went for MIG process. It was because of our financial limitation. It is not by our choice that we clubbed on the same system material addition and subtraction. We didn't simply have any other option, so we had to go for it. Now I'm going to tell you about a third bias I have. When you talk about MIG welding process, everywhere in the world, in the automotive industry, people use robot welding. Robot is very common tool for welding operation, and what we adopted for cladding is nothing but the MIG welding system. So robot would have been the easiest and natural choice, but I went for CNC machine. That is because I was a CNC programmer in Hindustan Aeronautics Limited. So I was more comfortable with that. I had not even played with any robot till that time. Very recently also, I have only seen the robot being in operation in close proximity, but I have never played with a robot myself. Whereas with a CNC machine, I have played myself a lot. So CNC was my natural choice. But then some of my choices turned out to be very correct. Some of them turned out to be pure biases, which I'm trying to overcome. So the point I'm trying to make here is we have to be very careful to evaluate. First of all, we have to identify our biases. Once we identify the biases, we have to assess whether the biases are good or bad. If it is good, develop upon them. If it is bad, try to bypass them. So this idea of HLM was conceived way back in 1996 or so, within 2 years of my joining. And then in 2001, we were able to get 26 lakh money from, in those days it was called DOE, Department of Electronics. Subsequently, it was renamed as MIT, Ministry for Information Technology, or Department for Information Technology. It kept on going through a lot of change in names. They called it as MICT. Today, it's called DAITY. Okay, so that is the funding agency which funded us. Many people are surprised because it is meant for supporting electrical and electronic related activities, but they had a division called Industrial Applications Division. That division looked at various applications, including the civil engineering people used to take projects for road transport and road signaling and all that. So we are grateful to DAITY for initiating our initial activities, and there was never any looking back. Started as 26 lakh. Today we have accumulated and spent close to 16 crore rupees over the last 24 years, which has now culminated in this machine called MSMA HLM. What you see in these figures, this is the CAD model which was developed by the company based on the conceptual design we gave. This is not our own design. We gave a conceptual design. This was further developed by the company. The company is called ACE Manufacturing Systems in Bangalore. So they developed it, and this machine today is available in this form. So this is during its developmental stage. Today it is available in this form. I'll show the video of it and come back because this machine is very close to commercialization. I have stationed 2 PhD students. We have hired a single bedroom house, stationed 2 PhD students there to do the integration activities. I was there last week on Friday and Saturday to review it. I've decided to go every week now and spend 2 days there to follow up the activities. I'll come back to these slides a little later. So this is the front view of the machine. These are the two side views. You see this machine from the top view. The machine on this side, it has a VMC, vertical machining center. Basically, it's a pair of VMCs looking at each other, amne samne. Okay, so you have one VMC here and another VMC here. They look at each other, and you see the Z motor of these. They together lift a long beam. This beam is more than 3 meters long, housing 6 tool posts there, which can be retracted or lowered by a pneumatic spindle. So the retraction and lowering traverse is about 300 millimeters, and the entire beam moves up and down over a traverse of 600 millimeters, which is our Z-axis. Now you see here a table which is called a Trinian table, which is actually B and C axis for our machine. Okay, the entire thing, and on this side we have spindle, on this side we don't put anything, but in future we may put probably friction stir welding on it. Otherwise, in these 6 posts, we can mount maybe MIG cladding system, we can mount a laser cladding system. We subsequently went for we bought a laser cladding system through an Indo-UK project. It was a 4 crore project. So we bought laser wire cladding system. This is probably the only one in the whole of Asia. It was developed by Fraunhofer Institute in Dresden. That is costing about 2.1 crore. So the worth of this entire machine today, if just the cost of it is about 4 crore, because the fabrication of the motion system itself is the purchase order of 1.4 crore. And the rotary table was about 32 lakh. So all put together, it will come to more than 4 crore. So we should sell it for maybe 5 or 6 crore when we do the technology transfer to the company. The same company, Ace Manufacturing System, is likely to sign the technology transfer. So we would like them to pay a one-time short to small payment, and we'll also work out a royalty. Now I'll show you a brief video which shows the machine.
Multi-station, multi-axis, high-frequency manufacturing machine.
So you see the omne-samne, 2 vertical machining centers. Only one has spindle. This is a Siemens 840D. It's a 5-axis simultaneous motion controller. This rotary table is an interesting rotary table. It is manufactured in India. In fact, the whole thing is a fully indigenous development, but for things like the controller and motors. So, this is made by a company called UCAM in Bangalore. I had a big problem during its purchase because they quoted something like 32 lakh, and the next higher quote was about 90 lakhs because other machines were all imported rotary tables. So only one company makes in India. So I had to really, justify to our audit, why is it so lower than the competitor? Okay, this also brings out another important point. Anytime when we try to develop a product indigenously, that will cost at least a third of the equivalent imported product. If we add more innovations, obviously you cannot completely reverse engineer a foreign product. If you add your own innovations, we have seen that in many cases the price can be divided by 10. So innovation will give a factor of 7, and import duty, transport, insurance, the foreigners' profit, all that will be a factor of 3. So we can develop indigenous products to 1/10, not reduction by a tenth, but 10% only will be the price of what we sell. We have proved it in a few cases. I'm going to show it a little later. So we needed to mount so many tools so that the complete layer can be produced. See, when you produce a metallic component, it's not as simple as plastic part. The heat involved is so much, the stress, not only the energy consumption, the energy being deposited in a non-uniform way leads to residual stresses. The non-uniform heat leads to, as it solidifies, it leads to residual stresses, and these residual stresses in additive manufacturing is it is tensile in nature. And additive manufacturing is a unique process where we suffer extremely high aspect ratio. Unlike machining, where you start with the bulk of raw material, here you put a raw material in a layer by layer manner. That means the aspect ratio is dimension in X or Y over the thickness. So it can become as much as 2,000 to 20,000 times. So it becomes a big problem. It leads to warpage, and in worst cases like hard materials, it results in cracks also. You know, one professor told me during my early stage that I'm doing it. He told me, Karunakaran, never do tool steel. It will crack into 2 pieces. I laughed at him. I told him, sir, how can a metal piece break into 2 pieces? He told me, keep it for 10 days and then look at the piece again. And I did the same after almost 10 years. I still remember his words. You know, the residual stress can be that much catastrophic. So what we do is, on the same machine, we try to reduce the residual stress by preheating using an induction heater, which will be on the right hand. And after the residual stress is minimized, after the layer is clad, we go for hammering. You know, we have a pneumatic hammer, a very cheap 2,000 rupees hammer. It works very effectively. Okay, I'll come back quickly. So I mentioned that it's a multi-station, multi-axis system. Multi-station, you have seen it. There are 7 stations, 1 milling and 6 tool posts are there. On the right side, we may probably add the 8th one, which will be the friction stir welding for additive manufacturing. It's not our requirement. We had an inquiry from a US university. A very young professor, he is keen to procure our machine. In that case, you know, he said, can we add a friction stir welding? So I said it's possible on the right side. So I would like to tell you that we have upgraded our hybridization to several levels. I told you that we initially started with material addition and material subtraction. You know, subsequently we expanded to several other levels. For example, on the same machine, we have make, TIG, as well as laser. That means for the boundary, which requires more precision, we will deposit in 0.5 millimeter layer thickness in 5-axis motion using laser cladding. we have a unique laser wire cladding system. Same wire will be used for laser cladding as well as MIG cladding. But MIG being very rough, we will use it for something like 1.5 millimeter. That means we will create the outer profile in 5-axis motion in thin 3 layers using laser. Then we'll have essentially a container. Into the container, we will use the MIG cladding to dump the material. So we'll have a best compromise of quality, cost, and time. So we are now combining different energy sources on the same machine. Of course, we have 2 projects for electron beam additive manufacturing. I'll discuss in the subsequent slide. We are not doing anything on the binder side of it. Okay, now that is a second level. So material addition and subtraction is one level of hybridization. Then combining different energy sources to create the same layer is the second level of hybridization. I will show the third layer of third and fourth level, namely combining 3-axis kinematics, 5-axis kinematics. Typical additive manufacturing machine requires only 2.5 axis. You move either in Z direction or you move in XY direction. So I call them as 2.5 axis. There are machines like I mentioned about this machine called photomasking, where it's a single axis machine because the XY motion comes from the mask itself. So there are also 3D printers which have only one axis. As against this, we have gone up to 5 axis or 5 degrees of freedom. In this case, degree of freedom and axis are same. Otherwise, they have different meanings. Then coming to the layering strategy, we again have different layering strategy. I'm going to explain it by going back to this slide. Here I'm showing some figures of the impeller. Okay, and I think my arrow is visible on the left corner of these figures. This is the CAD model of the impeller. Now the first vertical or column, we have 3 CAD model, the near net geometry achieved in this machine, and the finished machine. So in this, what we do, every time we grow the component in horizontal layers of something like 1 millimeter. You can't get 1 millimeter, so we deposit something like 1.2 or 1.5 millimeter and then face mill it every time. So every time we will preheat ideally, then do the cladding, if possible outer profile by laser and inner area by MIG. So after cladding and creating the layer, it will be very rough. It will have scallop surface, height control will be poor. So we go for face milling operation. Now, I told you that we went for MIG because of our financial limitations. Today, I find that people have even coined a term called WAAM, wire arc additive manufacturing. You know, a lot of researchers are developing WAM systems. That means whatever we selected because of our financial constraints proves to be even now worthy of it. So here in this particular part, we grew in horizontal layers. But then you see that in all additive manufacturing, you need some kind of support mechanism to take care of the undercut or overhanging features. You see the impeller, it is highly twisted blade. So what we drop are the molten droplets. So the droplets have to be captured in the appropriate place. So that is why we have the rotary table here. We rotate the B and C axis appropriately with appropriate XYZ motion so that the right place receives the droplet. So we have developed our own software for doing this. So in this particular case, the left 3 figures, it is horizontal growth in the horizontal layers, but 5-axis motion is used to alleviate the need for support structures. So this is a traditional additive manufacturing. Subsequently, what we thought, we can divide this impeller geometry into the hub and blade. Okay, as you can see, the hub is a simpler geometry which can be built on a 3-axis machine. So that's what we did. So this hub was produced on a 3-axis machine, and the blades were added in a 5-axis motion on top of this. So you see that it's no longer horizontal growth. The way all natural or biological systems grow, we start from chromosomes, and then we grow in layers, but these layers are no longer horizontal layers, they are conformal layers. That's where I'm talking about planar layers and conformal layers. So in this particular case, we could go up to the conformal layers, very closer to the nature. The only problem here is it is still not fully automatic. You need a human being to create the NC code with a lot of intelligence built into it, but it's still a lot of human intervention. We use Delcam. We have added some code on top of Delcam using its API. So, but fair amount of human intervention is still involved in this. So in our MSMA system, we have 4 levels of hybridization taking place: material addition and subtraction, different energy sources like laser and MIG. We have a 3-axis and 5-axis motion to realize objects like this. We have planar slicing for some components, and we can also go for conformal slicing. So this is a machine which evolved over the last 24 years of time, consuming about 16 crore of money, the latest being Imprint project. Imprint gave us about 4 crore money. So we were able to now nicely reach it. So we will very soon, probably in the coming IMTEX, coming in January, we will launch it. The machine is currently in Bangalore, so we will launch it during IMTEX in a commercial way. So I discussed about these 4 levels of hybridization. Similarly, on the right side, I have shown some items like we have a face mill on the spindle side, and it also has an automatic tool changer with about 20 tools. So on the same machine, we will be able to convert this near net geometry into final geometry. So now you see that all the abusive tools are mounted on the tool post, whereas the spindle is not disturbed. The spindle is also quite far away from the heat sources, and we will also have a hammer somewhere here. So nothing will be affected. So the machine will be intact. It will be protected from the heat from coming from the cladding systems and the hammering forces. So this can also maintain a precise machining accuracy for finishing this. So this is a truly hybrid system which will also do rough face milling as well as the finish milling. So with this, I'll conclude the MSMA part of it, which is our flagship project running for about 24 years and feeding all our expenses. Now you see we have evolved it to the next level. We call it now M cube HM, or you can say MXHM in the next versions. So here what we are doing is in one of the tool posts, we are adding a TIG cladding system with 4 wires coming from all 4 sides. TIG normally has a wire coming from a side, a single wire will come. So we have put 4 wires. Now these 4 wires, if they are of the, it will be about 0.4 to 0.5 millimeter diameter, very fine wire. And at the center we'll have the tungsten electrode. The tungsten power source is being specially developed for our need. It will be a high frequency power source going up to about 10 kilohertz of oscillation. So because see the wire will go inside, if the wire is of same composition, then it's okay. It will only add to the productivity. The deposition rate will be higher. What we are actually proposing is we will put different wires. For example, 2 of the opposite tubes can dispense titanium, 1 can dispense aluminum, and the 4th may dispense vanadium. So we will be able to produce titanium alloy, which consists of these 3 materials. This popularly is known as Ti-64, because titanium is 90%, 6 is aluminum, and 4% is vanadium is a typical composition, which is very popular in aerospace and medical applications. But there are applications where you may like to mix them up. have different composition at different points. So having a cladding system of this kind of multi-wire will lead to realization of heterogeneous objects. The heterogeneity can come from two nature. One is porosity itself can become heterogeneous, or you can have composition varying within the matrix. So far in 3D printing, we were talking about realizing a solid part. Only the surface geometry is important. Now we are talking about realizing heterogeneous matrix with variations inside the matrix in terms of porosity, in terms of composition. Now the nature of variation itself could be gradient or abrupt. When the variation is abrupt, you call it as a composite. When the gradient is smooth, you call it as a functionally gradient object. So our wire cladding system with multi-wire head being developed for us will be able to develop this. So we call it as M-Cube HM. We are submitted to IGSTC, Indo-German Science and Technology Center for funding in collaboration with a German partner. Let's see what happens. But this is our next goal. So in this context, when they were talking about the title of that, today they want to call it as 4D printing. So the fourth dimension is basically time. In this particular case, it is particularly referring to the smart materials, or what are known as shape memory alloys. Okay, so it's more of a material variation. The basic machine is still the same, layer by layer additive manufacturing. But when you use it for producing, it's like people say bioprinting. It is actually a 3D printer used for biological material like some kind of tissues. So they call it bioprinting. So today, when you use the machine for printing the shape memory alloy, you call it as 4D printing, because under the influence of some stimulus, it changes its geometry. So they call it as 4D printing. In fact, you can extend it. You can extend it for many things, as you have already seen. Professor Ahuja also pointed out, you can go for 5D, 6D, why only D? You can call it as degree of freedom. You can call it as axis and so on. For example, this particular machine, if you look at it, the kinematics will be the 5-axis machine, and then we have 4 wires coming, and you have 4 wire feed velocities. Okay, the wire feed rate has to be different as the 5 degrees of physical motion is taking place for the torch. That means in this particular machine, you will have 9 degrees of freedom happening. They are not 9 axes, 9 degrees of freedom and 9 axes happening. Now, nothing prevents you to add more number of nozzles, dispensing more number of materials. So you have now MX HM coming up. So this is typically on wire cladding system. You can also think of powder bed and various other, there are at least 7, 8 different approaches for additive manufacturing. So each of them can have different method of doing it. Now I'll quickly highlight on some of our other interests. Currently, we are executing projects worth about 25 crore. Interesting thing is, most of them are funded 25% by private organization. For example, I have 3 Untitled Avishkar Yojana projects, each about 5 crore, so 15 crore. And I have a DST project on advanced manufacturing technology, where L&T is our partner. We are developing an electron beam wire cladding based additive manufacturing system. So this machine is for thermocol. What you see in white color is a thermocol piece. Now we don't follow the traditional thin layer manufacturing here. It's a very simple machine. You see the thermocol piece built on this machine. You see the gluing point. There are only 3 layers on this machine. The entire thermocol is in 3 layers. So this particular component, it actually doesn't fit into the basic definition of layer so far as we know about additive manufacturing. When you say layer or slice, it will have equal geometry at top and bottom. It will be very thin. Whereas in our case, it is very thick, and the top and bottom geometry of the thick layer is also different. So we didn't want to call it a layer, we call it a segment. Okay, so we call it a segmented object manufacturing. It's a very interesting machine we developed about 15 years ago for gas turbine research establishment. So they funded it to about 45 lakh. Today we have also got a UAV project in which we will convert the thermocol into metal casting. We are establishing a foundry, foam foundry. For this we call it the rapid foam foundry. It's a 5 crore project. We also developed with the help of another company in Aurangabad, Grindmaster. They gave us 25% money. It's another 5 crore project. We developed a 3D printer for sand. This is a sand mold we built out of this machine. We have 3 versions of the machine. One will make use of a cheaper CO2 laser with flying optics. Another will make use of still flying optic, but 4 kilowatt laser with a linear motor for fast traverse. Third version will make use of a galvanometer for XY control, and it will be about 600 watt laser. So we have 3 versions of the machine. This mold was made out of the first version of the machine, and this is a casting produced out of that. You see that when you say sand mold, immediately poor accuracy comes to our mind, and a rectangular or cylindrical block of mold comes to our mind. Here you see that we have a conformal mold. It has 2 advantages. One is the building cost comes down. Second is during the solidification, the heat transfer also will be very uniform. So a lot of disruptive benefits are coming through these technologies. Now here I have a very interesting project. It's not funded yet. This machine is our ICE 3D printer. Okay, very recently, I think March or April, my student succeeded in building ice out of it. This ice was not built on our machine. It was made on a silicon rubber mold, but this was built by my student in March or April. That boy is a very crazy boy. He said he will do only ice 3D printing. He was not ready to accept any other PhD topic, so we supported him. Otherwise, there's no finance available from any funding agency for it. He tried different levels of, freezing. Finally, he ended up with liquid nitrogen cooling. We are still toying with the 2 things, liquid nitrogen or solid carbon dioxide. Of course, it is augmented by the traditional cooling system. Like a refrigerator. It has a refrigerator inside or freezer inside which can sustain the temperature, but in order to get the quick cooling, we use liquid nitrogen. Right now, we also tried many things, even water tube we tried, but that consumed a lot of air, so we gave up. Okay, now we took the ice, created a plaster Paris mold, created a casting out of it. We used, drying always happens above 0 and above atmospheric pressure, whereas we went for sub-zero and vacuum. So it's a very strange thing, thinking of drying happening at inside a refrigerator. So that's what we did here. It has a name already, when we do the literature, we found out it's called freeze drying. Now the third set of projects, we have 2 projects, very interesting projects. EBAM, electron beam additive manufacturing. We have 2, one for powder bed technology and the other for wire-based cladding technology. Typically, you'll find that powder bed is suitable for very small but precise parts, and wire is suitable for very large and fast cladding, and it also is amenable for gradient deposition, as I have explained already. So this is funded by DST, and L&T is our partner, industrial partner. Here AMS is the industrial partner. So both of them have given about 25% of the money. So together for electron beam, we have about 11 crore funding available. Interestingly, IASC launched, I remember the exact date, December 13, 2019, they announced the development of powder bed based EBAM in competition with the only international company from Sweden, Arcam, but they are yet to show any physical component, and they depended on all imported technology for EB. we are going to do everything indigenously. You know, we have taken the technology transfer electron beam welding from BARC in Mumbai. We have signed technology transfer agreement, and this is under fabrication in Bangalore in a company called High Vacuum HHV, Hindustan High Vacuum. So it's under manufacture there. So we have a lot of dreams on electron beam additive manufacturing. We have recently renamed it as electron beam hybrid manufacturing, because in both machines we have added ATC, automatic tool changer, for doing the milling. We don't want to go through 0.1 millimeter or 20 micron layer thicknesses. We would go for 0.5 millimeter or 2 millimeter here, because, you know, additive manufacturing, you know, initially it was known as rapid prototyping, but that name is no longer valid. So they renamed it as 3D printing or additive manufacturing, because if you look at a CNC machine and a 3D printer is pathetically slow. Whereas we would like to make them as production machines. If they have to be production machines in terms of quality, cost, and time, they have to be matching the traditional process. So that is our focus. So finally, I'll come to the conclusion slide. Total automation is the foremost advantage of 3D printing. Subsequently, people realize some of the very interesting geometric and matrix capabilities of the system. On the left side, I'm showing some of the geometric capabilities. Assemblies can be realized directly. Very complicated ducts can be incorporated. Custom designs are possible. On the matrix side, functional gradient matrix, I was talking about it a lot. So functionally gradient matrix is one in terms of porosity, in terms of composition, or you can also make, today you have any material available for 3D printing. It started with polymer, but today you name any material, you have the material available for 3D printing. What they have in their libraries, commercially useful ones or popular ones, but if some organization needs a specific material, it's a question of time and additional money for which they will develop and give it. So 3D printing is possible today for any material. Therefore, I would like to confidently say that if we can model any geometry inside a computer system, we have the technology today using which can be 3D printed. So that is the claim I'm making here. With this, I'll conclude my presentation. Here I have a slide giving my personal details. So thank you very much for patient hearing. You can probably shoot this slide for future communications. As I said, network is very, very important, bidirectional networking. Thank you very much.
Thank you, Professor Karunakaran, for this elaborative talk. Dear participants, now the panel is open for discussion. If you want some queries, we can request Professor Karunakaran for answering those queries.
Should I stop sharing, sir? Sharing can be stopped now? I think they have taken, right?
Ji, sir. Right, sir. So, any participant, any query, please. You may unmute or can ask your query.
Should I look at the chat box? Normally they put it in the chat box. I see some. Oh, chat box has nothing except greetings. Is there any question?
Sir, I have two queries with me. Sir, we are trying with this DMLS.
Yeah, tell me, sir. Yeah.
So we are trying with DMLS for printing of 17.4 pH stainless steel. So what we observed while printing in a metal printer, what we observed that specifically once we are interested in getting a some sort of a screw profile, so the dimensional accuracy is a challenge, right? Because we have to provide the support to the metal part. So we tried with different configurations and we try to explore why this is. So the manufacturer is saying that for getting some threaded profile over a metal part, it's not that that good in metal printing.
Are you talking about Phoenix machine which we bought?
Yes, sir.
Phoenix 3D systems.
3D system, sir.
Okay. What is the layer thickness you are printing? 30 microns or something?
Sir, we tried with different layer thicknesses uh, as per the availability in the schedule. But the problem is like model and the sport material is same, and then I have to go for the EDM wire cut of that. Probably the screw profile is really we are facing a challenge specifically in the assembly bit.
You are talking about screw profiles, huh?
Yes.
Okay. See things like what is the size of the screw? Is it like extrusion screw or a normal screw? Is it for extruding something like plastic extrusion?
No, sir.
molasses?
Like you just shared one last slide, na, in which you were showing some barrel sort of thing in which the outer profile was there, right? So that simply M10 and 1.5 pitch, something like that.
See, what is happening is number one, if you look at any of the screws, the surface finish is extremely high, and the screws also. You take any screw, the complete load of the screw is borne by only the threads. So, in fact, I would say that every screw or fastener can have a central hole drilled, because the center part doesn't really take any load. It is always the thread which takes the load. So both for fastening purpose, for ease of fastening, and for fatigue life, the surface finish of the thread is very important. So I would definitely recommend not to make the thread on 3D printer. You should make a complete barrel of the shaft, and then thread rolling should be done. 3D printer is not suitable for some of the features. That is where we have to go for the design for additive manufacturing concept. One of the concepts we can blindly take is, because of 0.1 millimeter layer thickness, you will get a stair step effect. See, when you talk about M10, the module may be, let's say, 1.5 millimeter. The pitch of it may be 1.5 millimeter. So you have a very small thread surface. So there will be 5-6 stair steps coming there. So surface finish will be pathetic. That will affect your fatigue life. And when you have each thread is a cantilever load. Okay. So every stair step will become a stress concentration point. So it will lead to failure of the thread. So it is not a good idea to make thread out of 3D printing. We should make a large size shank on it. Go for either thread cutting or thread rolling is better. Rolling has much better fatigue life compared to thread cutting. This is one of the most important guidelines on design for additive manufacturing by a lot of people.
Okay. So there are two questions in the chat box. One is how 4D printing is different from 3D.
Okay, I tried to explain. According to me, it's only the material difference of. I gave the example of bioprinting. Tissue is extruded through the syringe, and then they deposit layers to produce people have printed ear on top of a mouse. But that is basically 3D printing, but the raw material used is tissue material. Similarly, you use wire form of the shape memory alloy. Okay, only the material is different. So at the time of printing, you are producing a single geometry. But at that time, there's no stimulus acting on it. So when you subject the same part for stimuli, then you get a different shape as desired. So it is 3D printer used for this special material called shape memory alloy. That is in my opinion. So yesterday, I once again tried to go to Google and then try to understand definition from different people. This is what they say. So it is a route for manufacturing shape memory alloys.
Okay. Sir, in the morning session, Professor Uja was talking about 5D also. So,
yeah.
So that means we are adding more stimulus, or this is something different?
So, sir, stimuli is not added during printing process. I showed our case where we use, let's say, a 4-wire cladding system, TIG, tungsten at the center, and on 4 sides you have 4 wires coming, and each wire has to have a velocity by a unique motor. So it becomes a 9-axis machine. So you can say that it's a 9D. Again, the word D here stands for dimension, but you can also use D to denote degree of freedom. Because in our case, it becomes degree of freedom. 5 degrees of freedom define the surface geometry, and the interior degree of freedom is by the 4 motors. Now you can add any number of wires. So that many degrees of freedom will come there. So these are all variations, but the basic concept is the same. So if you really look at the way CAD/CAM systems evolved, first it was CAD. At that time, they even used the word D to denote drafting, because at that time it was 2D, only XY was possible. I worked 2.18 way back in 1986. It was just XY, you could not do 3D. Okay, it was called D for drafting. Then they started adding 3D, then it became FEA was possible. So it was called CAD, and then CAM happened parallelly by NC programming tool design. So CAD/CAM was there. Then subsequently what they did, from CAD, they retained only the modeling part of it, removed FEA, CFD, everything, Adams and all. It was added to what is called CAE, computer-aided engineering. Now, again, you will see that a lot of misnomers are happening. CAD is design, CAM is manufacturing, CA is engineering. And engineering includes design and manufacturing. Engineering is not something different, but people started adding terms, and they were the leaders in the industry. People accepted even if there were misnomers. For example, end mill आप ले लीजिए. When you say end mill never cuts with the end. End mill is efficient in cutting with the side flutes, but we call it as end mill. According to me, end mill is a misnomer.
Okay.
So that is how it is.
Okay. Sir, there are 2 more questions in the chat box.
Yes, sir.
One is on, is the friction welding is completed and fully functional? Have you started using friction stir welding?
Well, I'm not a researcher in friction welding. I have only bookish knowledge on that. See, friction stir welding is today a fillerless process. Additive manufacturing always requires a filler. I saw in a college in Coimbatore, what they have done is, typically friction stir welding uses a helical blunt tool which runs at the interface of 2 dissimilar materials to be joined. So what these people do, they take a substrate, they take a 10 millimeter rod, the rod rotates at something like 2000 RPM using a spindle, and very similar to the spool we use in FDM machine or any wire-based welding machine. So it also, using a pinch wheel, it pushes it down. So you have a rotating rod. When it is pushed down on the substrate, friction welding happens. So this is a different method of friction welding. So this is what is used in friction. You should not really call it as, okay, because it rotates, the word stir also is useful. So this is a friction stir welding where the tool itself is a consumable, very similar to the MIG welding process. So this is what people are looking at.
Okay, then sir, the second question was in continuation to this, are all these techniques applicable to 4D printing too?
Okay, as I said, 4D printing is just for a different material. When it is specific for smart materials, you call it as 4D printing. Otherwise, whatever happens to 3D printing, it is applicable to this, because it's nothing like a separate process. It's exactly the same, only the raw material used according to me is different.
I think, sir, okay, there is another question. What are the advantages we can get from 4D printing?
Okay, I think it's self-explanatory. It is for a different material. So this is a route to produce smart materials. You want to produce a sensor or something. Otherwise, these smart sensors are also made by other manufacturing processes, but 3D printing makes it more elegant.
I think, sir, the session is really useful, and we have, I think, covered all the aspects and all the questions have been answered. So let me thank Professor Karnakaran for the time spent for educating us, for giving us the input in this wonderful area. So from Little Chandigarh side, we are really thankful to you for acceding our request to be the keynote for this session. Thank you, Professor Karnakaran. Thank you very much.
Thank you, sir. It's my pleasure. Good luck to everybody. Good day.
Yeah, thank you.
I'll sign off. Thank
Yeah.
you.
So, dear Professor, we will take a short break and the next session will start at 12.